Hello, everybody, again, and welcome to your channel, Thermal Engineering Concept and Principle. Here, I will continue to introduce to you a briefing for the uh, mathematical treatment of heat generation physics in a plane wall. The first part. In the last episode, we talked about some of the boundary conditions related to solving the one-dimensional steady-state heat conduction with heat generation in a plane wall. Here, in part two, we will continue to give the briefing for such applications to include other boundary conditions. Thank you for your support and encouragement to continue the main objectives of the channel and its content. Let us introduce the main objectives of the present episode. The main objectives of the present video are related to the one-dimensional conduction heat transfer, as we have discussed that before in the first part, where the plane wall experiences a heat generation per unit volume. Here we will introduce the convection boundary condition where the wall is exposed to a fluid adjacent in specified temperature and heat transfer coefficient. We will use another boundary condition which is related to the constant heat flux at the surface of the plane wall under steady state conditions, of course. And then we will approach the final part as usual, as the closure for the present episode. Can we reduce the general form of the uh, three-dimensional heat conduction in um, solid material? One of the most interesting forms of this equation is the one-dimensional steady-state heat transfer. And this form of equation has many applications in industry, or we may minimize the effect of other dimensions, so we will consider the heat process to occur in one direction. The general form, as has been presented by equation number 2. How can we reduce this equation to the form of um, one dimension? As shown in this figure, we have the faces and we may consider it as element with a thickness of L. And if we ignore the effect of y direction, then that means partial square t with respect to y square will vanish and approaches 0. And in the z direction as well, we may have um, partial square t with respect to z square equal to 0. And that will yield a form of equation where can be applied in the one dimensional form, heat conduction with heat generation. And this is called the transient form, which is represented by equation 2.1, partial square t with respect to x square plus q dot divided by k equal to 1 divided by alpha partial t with respect to tau. And this form of equation um, it's a general form and can be used even for the case where there is no heat generation. So for steady state, you will get the right hand side will go to 0. That is the temperature doesn't change with time. So we have partial t with respect to tau is equal to 0. And the final form will be d squared t by x squared plus q dot divided by k equal to 0. This is the general form for steady state conduction heat transfer with heat generation. To use this equation and to find a solution, we need to execute an integration. The first integration will give us q dt by dx plus q dot divided by kx equal to 0. And if we conduct the second integration, we will get t of x as a function of x plus q dot divided by k x squared divided by 2 equal to c1x plus c2. This is a magic equation where it is used in the one-dimensional heat transfer with heat generation and can be used regardless of the boundary conditions. So I will call this equation a magic equation. Now let us consider a convection boundary condition that the wall is exposed to a convective thermal fluid, and the figure shows that one side is adiabatic and the other one is exposed to a convection heat transfer uh, process where we have thermal fluid. It could be air, oil, or whatsoever. And the solution for this equation, we again start from the general form of the one-dimensional heat transfer by conduction with the heat generation under steady state conditions, which is represented by equation number 3. Then we have equation 6 from the previous example that t of x equal t w plus q dot divided by 2k l square minus x square. And for the steady state condition, we have the total heat generation in the wall equal to the amount of heat convection dissipated to the ambient. Then we have Q dot times A times L equal to HA times delta TW. And we have T sub W equal to Q dot L divided by H plus T of the ambient. And equation 6, which represents the temperature distribution in terms of TW, may be used with equation number 7 to get the final form in terms of the convective heat transfer fluid, that is in terms of the H and TA. So we get T sub x of x equal to Q dot L divided by HA plus Q dot divided by 2K times L square minus X square plus TA, which represents the final form of this equation. And this is the answer for this example. For verification, we may also obtain the same results if we apply the following concept of the wall exposed to convection, that is heat transfer rate by conduction at x equal to L equal to heat transfer rate by convection at x equal to L. If we substitute these values, we will get minus K A dt by dx at x equal to L equal to HA times TW minus TA.
Now let us consider a case study where a convection boundary condition for the wall uh, where it is exposed to a fluid having temperature Ta and H sub A. And now for the figure or the plane wall which is shown uh, in this illustration, one side is adiabatic, which is insulated, and the other side is exposed to a fluid. And the question is how to find the temperature distribution in terms of the convection parameters. The solution for this uh, case, we should remember the general form of the question for the heat transfer, where in one dimension with the heat generation for steady state, which is represented by equation number 3, d squared T by dx squared plus q dot divided by k equal to 0. And let us consider equation number 4, which represents T of x equal plus q dot divided by kx squared divided by 2 equal to C1x plus C2, which has been obtained from double integration of equation number 3. We have a boundary conditions for the insulated side of the wall. We have Q minus K A dt by dx equals to 0, and that will give dt by dx at x equal to 0 equal to 0. If we apply this boundary condition in equation number 4, then we will get C1 equal to 0. And if we consider the boundary condition at x equal to L, and let us consider the temperature there is T sub W, then C2 equal to T wall plus Q dot divided by K plus times L squared divided by 2. And if we substitute that in the general form of equation number 4, then we will get the temperature distribution in terms of the wall temperature and the heat generation per unit volume as represented by equation number 6. If we continue the derivative, we have the heat transfer rate by conduction at the wall surface, which is exposed to convection at x equal to L, equal to the same amount of heat transfer rate by convection at x equal to L, which represents the steady state condition for heat transfer. And if we substitute the values, then we have the conduction part equal to H sub A times delta T, which represents T sub W minus TA. And at x equal to L, if we substitute the values, then we will get dt by dx at x equal to L equal to H sub A divided by K times TW minus T sub A. And equation 6 will be dt by dx equal to minus q dot divided by k times x, and if x equal to L, then dt by dx at x equal to L equal to minus q dot divided by k L. Equation number 8. Therefore, equation 7 and equation 8 produce minus HA times TW minus TA equal to minus Q dot divided by KL, then we will get T sub W equal to Q dot L divided by HA plus TA as represented by equation number 9. And this will produce, when we substitute the value in equation number 6 for T sub W, then T of X equal to Q dot L divided by HA plus Q dot divided by 2K times L square minus X square plus TA, which represents the final solution for the temperature distribution for the wall, which is exposed to convection and one side is insulated. For verification, dt by dx equal to minus q dot divided by kx, and if we have x equal to 0, then dt by dx equal to 0. And if x equal to L, then T sub W equal Q dot L divided by HA plus T sub A. And these are the boundary conditions which has been fulfilled by the general form of equation number 10. And now let us derive an expression for the maximum temperature in the wall of the previous case study, and that means when the wall is exposed to convection and it's insulated as shown in this figure, then we will need to find the maximum temperature, the position of that value for the maximum temperature and where it is. And the general form is again d squared T by dx squared plus Q dot divided by K equal to 0, which represents the one-dimensional heat transfer in the plane wall where there is a heat generation and a per unit volume under steady state conditions. We have equation number 10 as represented in the previous example. Then we may find the maximum temperature from equation 10 by visual evaluation. For this equation, the maximum temperature occurs when L square minus X square is maximum, since all other values are constants value. Temperature of the wall, Q dot, thermal conductivity, the thickness of the wall, heat transfer coefficient, all of these parameters are constants. Then maximum temperature depend on L square minus X square as a maximum. And if we have X equal to 0, then this value L square minus X square equal to maximum. And then the answer for Tmax equal to Q dot L divided by H sub A plus Q dot divided by 2K L square plus TA. This is the answer for this example. And another way is to get the maximum temperature by taking dt by dx equal to 0. And if we take dt by dx from equation 10, we have dt by dx equal minus q dot divided by kx, and equate that to 0. Then we will get Tmax equal to q dot L divided by HA plus Q dot divided by 2K L square plus TA, which is similar to equation number 11. And this is the answer for this equation and this exercise. And then the maximum temperature occurs at the insulated side of the wall. Let us talk about a boundary condition where a constant heat flux is directed to one side of a wall which experiences a heat generation, and the other face or other side of the wall is exposed to convection, where a fluid is passing with a temperature T ambient and a heat transfer coefficient of H sub A. The solution for this equation, again, we should start from the general form, one-dimensional heat conduction, uh, which is accompanied by a heat generation per unit volume in the wall in one-dimensional form under steady-state conditions. d squared t by dx squared plus q dot divided by k equal to 0. And we have applied two successive integrations. So we have obtained the form of equation 4, which represents the temperature distribution in terms of the position, thermal conductivity, heat generation, in the form of equation form, that is T of x plus q dot divided by k x squared divided by 2 equal to C1x plus C2. So to solve this equation, we need two boundary conditions to find C1 and C2. The first boundary condition is at x equal to 0, where q equal minus ka dt by dx. And if we apply the flux of heat flux at the surface, then we will have dt by dx equal minus q dot divided by ka equal to minus f divided by k, and that means q divided by a is the heat flux that is directed to the surface. And then if we take this expression and use it in equation number 4, then we will get a form for C1 equal to minus F divided by K. Also, we have a boundary condition at X equal to L that the temperature equal to T sub W. Then T sub W plus Q dot divided by K L squared divided by 2 plus FL divided by K equal to C2. If we substitute the values of C2 and C1 in equation number 4, then equation number 5 represents the temperature distribution inside the wall, which is exposed to a heat flux, that is T of x equal to T sub W plus Q dot divided by 2K times L squared minus X squared plus F divided by K times L minus X. And if we have a look at the boundary condition number 1, which we have used, that is dt by dx equal to minus q divided by Ka, and the q divided by A represents the heat of flux, which is equal to F. And the equation number 5 is the final solution for this equation. And if we have another example for this type of boundary condition, let us consider a surface or a wall that is exposed to constant heat flux, and the other side is exposed to convection, and we have a heat generation Q dot in units watt per cubic meter with the parameters of the convective side, then the question is how to find the temperature distribution in the solid wall in terms of the convection parameters. That means in terms of T sub A and H sub A. The solution, again, we have to start from the one-dimensional steady-state heat transfer equation. D squared T by dx squared plus Q dot divided by K equals to 0. And two integrations will produce equation number 4. And we need to apply the boundary conditions when x equal to 0, dt by dx equal to minus f divided by k. And we have also when x equal to L, T of x equal to T sub W. If we apply these boundary conditions, we will get the temperature distribution in terms of TW. And we have this solution from the previous example in terms of equation number 5. Now, how can we substitute the value of T sub W in terms of the convection parameters, and that will lead the final solution of this example. So the heat transfer rate by conduction at the convective wall at x equal to L equal to heat transfer rate by convection, which is at x equal to L as well. If we substitute the values, then we have the conduction part minus Ka dt of x by dx, and where x equal to L equal to h sub A times A Tw minus Ta. If we continue with the solution, then we will get x of L at x equal to L dt by dx equal to minus h sub A divided by K T wall minus T ambient. Equation number 5 gives dt of x by dx equal to minus q dot divided by kx minus f divided by k. Then if x equal to L, then dt by dx is represented by equation number 7. So if we use equation 6 and 7 for dt by dx, where x equal to L, then we will get this form of equation which produces Tw, which represents the wall temperature, equal to 1 divided by H A times Q dot L plus F plus Ta, which represents the wall temperature. So if we go back to equation number 5 and substitute the value of T sub W, then we will get T of x is a long expression, but again, it's the correct one. T of x is represented by equation number 9, which represents the temperature distribution 1 divided by H of A times Q dot L plus F, close the bracket, plus Q dot divided by 2K times L squared minus X squared plus F divided by K times L minus X plus Ta, which gives the final expression for the solution of this exercise. Dt by dx equal to minus q dot x divided by k minus f of k. That means if we take the dt by dx from equation 9, then we will get equation 10. The verification for this equation, dt by dx, which is represented by equation number 10, if x equal to 0, then dt by dx equal to minus f divided by k, which is the same as we have explained during this derivative, which represents the boundary condition number 1. And we have if x equal to L and substitute x by L in equation number 9, then we will get T sub W equal to 1 divided by HA times Q dot L plus F times TA. And then this is the boundary condition number 2, which is also is verified and fulfilled by T of X, which is represented by equation number 9. The closure of the present episode, we passed through the derivative of temperature distribution in a plane wall under steady state conditions for the one-dimensional case, and we used different boundary conditions on both sides of the wall. We introduced boundary condition related to the constant heat flux and convection boundary condition, and we have expressed the mathematical treatment of the first or the one-dimensional heat transfer in a plane wall. And finally, I have to mention that there is a group of references that can be used in a link in the PDF version is listed in the description box of the present video, and thank you for watching. And if you think that the information presented here are useful to you and others, please subscribe and share the information with your friends to achieve the most important aims of the present channel and its content, is that to let the information reach who needs them freely. And I hope I will see you in next episode with different application of heat conduction, heat transfer. Bye-bye.